Hey guys, I hope you guys are doing well. Just want to say I really appreciate the work that you've been putting in to finding these integrals. It's not an easy thing. One thing I haven't even told you yet is there's some integrals we simply just cannot find. Nobody's been able to find the antiderivative of certain integrals. Now, I haven't given you any of those, but I do know it's been a challenge, and you're not alone. This is a challenging concept. And there's just a lot of decision making that goes into it. And our next step here is to be able to identify from just a random integral what technique is going to be our best option, and how do we try that, and where do we go. Everything so far has been, here's a technique like integration by parts, and then here's your integration by parts practice, right? And here's trig substitution, here's your trig substitution practice. Well, once we get beyond in these techniques where we've learned them individually, integrals are going to pop up, and we're going to have to be able to work with them. And we're going to not just be like, oh, today is an integration by parts today, so we're going to do integration by parts. So in our review that we're starting today, no more techniques. We've covered every technique that's going to be on your next test. But now we need to work on selecting the right method. So we're going to do a review of all the techniques, and we're going to talk about what are the things that we look for, and then we're going to look at some examples of how that decision-making process works. All right, so with our techniques here, going back to our first kind of special technique, it was actually on that the last test here, and was one that we found to be very useful, was substitution. Right? Let u equal something, change your variables over, get it into an easier antiderivative, and you've got it. Now, I'm not going to spend time talking about what to look for quite yet because I want to get through the whole list. Secondly, we looked at integration by parts. We have our u, we have our dv, we solve for du, we solve for v, we set up with our integration by parts formula. Our third technique, trig substitution, which I think is one of the more clever techniques that we've looked at, where we let x equal something with a trig function like sine of theta, cosine of theta, tangent of theta, secant of theta, something like that. Division, we didn't really spend much time on. I just showed you, I think, one example in a video because it's something that we did before, but I do want to talk about this as we review today, where we take the numerator divided by the denominator using long division or synthetic division if possible. And then lastly, we had partial fractions, which is what we can use when division doesn't work. And, well, let me not get into that quite yet. So, substitution. When do we like using substitution? Hopefully, kind of the key word that comes, that's showing up in your mind right now when you think about substitution is a composite function. When we have something inside of another function, we like to let u equal that inside and see what happens. Now, when we change the variables, we hope that the rest of it kind of cancels out or cleans up significantly. So, for example, we might let u equal x squared, then we find du equals 2x dx, and the x's cancel. We get all excited because it just cleaned it all up big time. So that's our substitution. Now, integration by parts is set up to help us with a product, right? U times v minus the integral of v du is what we set up when we have the integral of u dv. Yeah, u dv is when we use that. Now, sometimes we use substitution with products, but when we use substitution with products, like I said, we hope when we change the variables, things cancel out and we no longer have a product. Integration by parts is something that we can use when substitution doesn't work to cancel anything out in a product. We'll talk a little bit more about integration by parts, but we kind of look for a product there. Trig substitution. Now, when we do trig substitution, we're usually using a Pythagorean identity. Okay? So we like to use trig substitution when we have anything that looks like it might be related to the Pythagorean theorem, where we have something squared minus something else, or something squared plus something else, something that reminds us of the Pythagorean theorem. Next one, division. We use division when the degree of the numerator is greater than the degree of the denominator, and we can just divide it out, and then we get each individual part, and then we have the remainder, which usually is going to involve a natural log, not always, but usually involve a natural log to get that last piece. And then lastly, we have partial fractions, and that's when the degree of the numerator is not greater than that of the denominator. And we can split it up into several fractions. We can solve for the numerators and handle each of those fractions then individually. Now, as I talk through this, I really am trying to avoid using the word always. None of these are you see this, you always do that. It just doesn't work that way, right? I mean, sometimes you have products that are solved by substitution. Sometimes a trig substitution is actually a product. Sometimes a trig substitution is part of a composite function. It just doesn't always work out that this means that. Okay. But we should be able to come up with what we think might be the best option. And one practice that you'll get really good at as you do these is maybe doing the first couple steps of substitution, or the first couple steps of a trig substitution in your mind, and start to see how it plays out. And if it's feeling okay, then you run with it. And if it's hitting roadblocks, then you say, okay, let's try a different direction. So it just takes a lot of practice, and it takes a lot of perseverance. And it is okay to try a technique for it not to work out. All right, trying to think what else I was going to say with this. I had a thought there somewhere in there. But it's not coming to me. Okay. So anyway, this is where we're at. These are the techniques that you have to be able to show me that you can do on your next test. We're not going to add any more special techniques, so more integration stuff coming up after this test. But let's just work on this. So what I have here is I have a whole bunch of integrals. And let's see if we can't identify what technique would be our go-to technique. So let's start on the first one. Okay. Now, I remembered what I was going to say on this last page. It is something I've said before. Remember, don't try a more complicated method, okay, if you haven't ruled out a simpler method. For example, do not do trig substitution before determining if a normal substitution will work. Trig substitution is much more complicated than a normal substitution. So always try a simpler technique first. And then one other thing I was going to say is there are some different flowcharts that can help you guide through this process. And if you want to make a flowchart, maybe using some of this, you're welcome to do that. But with all the flowcharts, there's not one that I love really more than another. If you want to Google integration techniques flowchart, you're going to find some options out there. You might find one that you like. If you want to make your own, you can do that. Beware if you Google it, there are some flowcharts that are put in there for comedy's sake, just because knowing that integration is really difficult. So just a little warning. There might be some inappropriate language in some of those, so just skip over those, okay? All right, so let's get to this list. First one. All right, here's what I'm noticing right away. Product. All right. Product. That makes me think integration by parts. But before I jump in integration by parts, I better make sure that a normal substitution doesn't work. If I let u equal x cubed, du is going to be 3x squared dx. And when I substitute that in, nothing really good's going to happen here. That e to the x is still going to be hanging out. Nothing's going to cancel out. So with this product, my first thought is definitely integration by parts. Now let's go to this second one. Hey, I see a product again. Okay, I see x times the natural log of x squared. So I might be tempted to jump into integration by parts. However, don't try a more complicated technique unless you've ruled out a simpler technique. I do notice I have a composite function. I have x squared inside the natural log of x. If I let u equal x squared on this one, okay, du is going to equal 2x dx. So du over 2x equals dx. And what's going to happen with this 2x and that x right there? The x's are going to cancel. We're going to have the natural log of u dx with a 1/2 out in front. So this is one that I would want to use just a normal substitution. All right, let's go to this one. Now down here I see something that reminds me of the Pythagorean theorem. I see a square root, I see an x squared plus something, so that makes me lean towards trig substitution. However, would a normal substitution work well on this one? Well, if we let u equal x squared, just like in the last one, if I solve for dx, dx equals du over 2x, right? And notice this x is going to cancel one of those, and we would end up with an integral of x over the square root of u. Okay, we'd have a 1/2 in front, and we'd have a du right there. Now, what about this x? Well, we know u equals x squared, so x equals the square root of u. Okay, but then if we take a square root, we need a plus or minus. Things are getting a little weird. It might work out, but I don't think I like what's happening here, especially with that plus or minus. Okay, so my technique that I would probably go to on this one would be a trig substitution. Okay. If I can get this to be a Pythagorean identity by letting x equal something, okay, so that I end up with a Pythagorean identity, I think that would be my go-to on that one. How about this one? Well, again, it reminds me of the Pythagorean theorem. Okay. A normal substitution would produce an x somewhere that wouldn't cancel out with anything in the denominator. I think this is actually a simpler one than the first one. I would go trig substitution on that. All right, this one. The inverse sine or the arc sine of x dx. There's nothing to do a substitution with. It's interesting, sometimes students like to say things like, well, let's let u equal x. Well, that's not going to get us anywhere. That's just going to give us the inverse sine of u du instead. So there's nothing to substitute. There's no composite function. Thinking about my other techniques here, it doesn't look anything like a Pythagorean theorem. There's no division in it, so it's not division or partial fractions. So that only leaves us one technique. And I want to remind you guys here that integration by parts can be used, okay, even though it doesn't look like a product, because the sine, the inverse sine of x dx really is a product. We do have the inverse sine of x times dx. So I would think integration by parts here would do that. We actually did this one a while back. Don't forget it's an option even if it only appears like it's not a product when it actually is. All right. Taking a look at this one, we have a fraction where the degree of the denominator is bigger than that of the degree of the numerator. We can't use division. If this was a cubed up here, we could use division. The degree of the denominator is bigger, so we are going to say that this is going to probably be a partial fractions problem. If I try to use substitution, like if I let u equal the entire denominator, du dx equals 6x plus 4. Oh, look at this. Dx equals du over 6x plus 4. And actually what ends up happening here? So I was so close to saying, let's do partial fractions. Okay? But because I took a little longer of a time to check to see if substitution would work, I would be paid off greatly. Okay? These would cancel. We would end up with the integral of 1 over u du, and it's simple. Think about how much more work partial fraction is than that. Partial fractions is a lot of work. So just take that minute and see if substitution works. Now on this last one, I better make my note here. That's a substitution problem, even though it didn't appear like it right away. Now on the last one here, let's see here. If I take the derivative of this, I'm going to have a 2x plus 10. That's not going to cancel out anything there. If I take the derivative of this, I would have a 12x plus 45. That's not going to cancel out anything. Plus, we got that x plus 2 hanging out. So after exhausting the possibility of substitution, this is one where we're going to have to go with partial fractions. All right, so I hope this is helpful for you. Good luck in your integrating. See you later.